So far, we've seen how Amdahl's law can be used as a simple model of an application to give us the upper bound of performance as we increase the number of cores. Now, it's important to remember that Amdahl's law gives us the upper bound on performance. It doesn't actually predict the performance of an application. It just gives us the envelope. But what it does explain is that if we have a speed-up graph where we have the number of cores on the x-axis and the speed-up on the y-axis, Amdahl's law explains why an application may start off with linear scaling, but then eventually plateau to a fixed value. And this fixed value is described entirely by 1 over the sequential portion of an application. Now, that gives us the upper bound, but it doesn't explain why some applications start to fall off as the number of cores increases. And to explain this, I like to describe what I'll call Amdahl's modified law. So you recall that Amdahl's law says that the runtime of an application on n cores is equal to the sequential part plus the parallel part divided by n cores. Now I'm going to modify this to have an additional term. So let me put a prime there to indicate that this is Amdahl's law modified. I'm going to add an additional term, which is some constant multiplied by the number of cores in the system. And that term is going to encompass all the overheads that can occur as we add more cores into the system. Now, what sort of overheads might there be? Well, there might be additional communication between each core. There might be data transfer to send tasks to different cores. There might be some latency to communicate between different cores. There might even be some bookkeeping that needs to be done in order to keep track of every core. So as the system gets bigger, we have more work to do to accommodate for those things, and that's going to be described by this term. Okay, so now if this is the runtime, then the speed up is simply going to be 1 over that value. Keeping in mind that we defined our task to have a unit time to begin with. And now, what happens if we take the limit as n goes to infinity of speed up of n? And again, let me add my primes here to indicate that's Amdahl's law modified. As n gets bigger, p of n disappears as before, but then k of n grows linear and gets bigger and bigger and bigger. And because of that, it eventually dominates over p of n. The denominator explodes, and the limit of this, as n goes to infinity, as 0. Now again, this is a model simply to encompass a wide variety of behavior, but it's sufficient to explain why for real applications we see that a speed-up curve starts off linear, it reaches some peak, but then eventually it falls off. So this is Amdahl's law modified. In any real application, there are overheads associated with scaling up, and so we always reach some peak, but then at some point the overheads of parallel computing overtake the benefits and our speed up falls to 0.